In this problem, we are asked to find dy dx using implicit differentiation. All right, so you'll notice here, so we're going to differentiate each term by x. Well, the first term has a function of x times a function of y. Two functions multiplied together, we need to use the product rule. So we'll have the first function times the derivative of the second. That's going to be cosine y. But remember that when you differentiate a function of y with respect to x, you need to multiply it by dy dx. Then over here, we will have sine y times the derivative of x with respect to x, which is just 1. Now, we did not differentiate a function of y here, so we don't need a dy dx. We differentiated a function of x. Now, with the second term, all we have is a function of y. So when we differentiate that, we'll get 4y cubed. Don't forget the dy dx because we differentiated a function of y. And then the x to the 6th, that derivative is going to be 6x to the 5th. We did not differentiate a function of y, so we don't need dy dx. So now what we need to do is isolate the dy dx terms, and then we'll solve for dy dx. So I'm going to pull this term over here, and this will leave us 4y cubed dy over dx here. And on the other side, we'll have 6x to the 5th minus sine y. Take out a common factor of dy dx. And now we can divide each side by x cosine y plus 4y cubed. And we get dy over dx is equal to 6x to the 5th minus sine y over x cosine y plus 4y cubed. In 2b, we have y minus tangent y minus sine x equals 0. We are asked to find the derivative of y with respect to x using implicit differentiation. We differentiate each term with respect to x. So the derivative of y with respect to x is dy over dx. The derivative of the tangent function is the secant squared of y. We differentiated the function of y, so that's going to be times dy dx. The derivative of the sine of x is the cosine of x. I'm going to pull the cosine x over to the right side. Factor out a common factor dy over dx. So the common factor dy dx comes out, we are left with 1 minus secant squared y, and then we divide each side by 1 minus secant squared y, and we get dy over dx is equal to cosine x over 1 minus secant squared y. In 3a, we are asked to find the second derivative of y with respect to x. So we will differentiate once. That would be cosine of 2x plus 1 times 2. We have a function within a function, so we need to use the chain rule. The derivative of the outside function is the cosine. The derivative of the inside function is 2. And so I'm just going to rewrite that as 2 cosine 2x plus 1. Now to find the second derivative, we'll use this chain rule again, in combination with some other rules. So we have 2 times the derivative of this cosine. Well, the derivative of the cosine is the negative sine. So I'm going to make that a negative 2 sine of 2x plus 1. So we've differentiated the outside function here, the cosine, and now we need to multiply by the derivative of the inside function, which is 2. That leaves us negative 4 sine of 2x plus 1. In number 3, we are given the equation x plus y equals y squared, and we are asked to find the second derivative of y with respect to x. Now, the direction should have said use implicit differentiation. So let's use implicit differentiation. First, we need to find dy dx. So what we'll do is we will differentiate each term here with respect to x. So it's going to give us 1. The derivative of y with respect to x is dy over dx. Here we're going to get 2y. Don't forget to multiply by dy over dx. Now, we need to solve this equation for dy over dx, so let's pull this term over here. So we are isolating the dy over dx terms. We factor out the dy over dx. And then we divide and we get dy over dx is equal to 1 over 2y minus 1. Now we need to differentiate that in order to get the second derivative. So let's think about how we want to differentiate this. We could use the quotient rule. We could also rewrite this like this. We could write this as 2y minus 1 to the negative 1, and I don't know, to me that just seems a little bit more appealing to differentiate this way. So if we differentiate this way, we will have negative 1 times 2y minus 1 to the negative 2, right? We're using the power rule. We're actually using the chain rule. So we're differentiating the outside function. Then we differentiate the inside function, or the derivative of the inside function is going to be 2 dy over dx. So I'm going to simplify this a bit. I'll call that negative 1 over 2y minus 1 squared times 2, and now dy over dx is 1 over 2y minus 1. So it looks like what we're going to have is negative 2 over 2y minus 1 cubed. We have 3 powers altogether of 2y minus 1. We have a 2 in the numerator and a negative 1. I think that's what we're going to get. In number 4, we are given the graphs of two functions, f of x and g of x. And we are supposed to assume that each of these squares, it measures 1 on each side. So it's 1 here and 1 there. So p of x is f of x times g of x. And we are supposed to find p prime of 1. Alright, so we need to find the derivative evaluated at 1. So, alright, so let's think about that. First we need to find the derivative. Well, this is p of x is f of x times g of x. That's a product, right? So using the product rule, this will be f of x times g prime of x plus f prime of x g of x. And now we just need to substitute in 1. So p prime of 1 is going to be f of 1 times g prime of 1 plus f prime of 1 times g of 1. Alright, so I think you already know how to find f of 1 and g of 1. You're given the x value of 1, and what you really need to do is find the y value. So this is a y value, and that's a y value. So when x is 1, let's see, f of 1 would be whatever that y coordinate is. I'm going to estimate it to be 1.5. We'll come back to g prime of 1 in just a moment. And I'm going to skip over f prime of 1 for just a moment and discuss g of 1. So we need the y coordinate on g when x is 1. So when x is 1, the y coordinate is negative 3. So now what we need is to evaluate f prime at 1 and g prime at 1. Well, these are derivatives, of course, and you remember that the derivative, especially when we're dealing with graphs, can be thought of as the slope. So what we need is the slope of f at 1 and the slope of g at 1. The slope of f at 1, let's see, looks good. It's going to be negative. So if we go from here to here, let's go from this point to this point. It looks like the delta y would be negative 1 and the delta x would be positive 2. So I think that's going to be negative 1/2. Actually, that goes right there. And in the other one, for g prime of 1, the slope here appears to be negative 1 all the way through there. So I'm going to put negative 1 in for g prime. I just came up with that just by inspection, just by looking at it, and I could tell that for every unit we travel in the for every unit we travel in the positive x direction, we go down 1 in the y direction. So you'd have a delta y of negative 1 and a delta x of positive 1. So dy over dx is the slope, and that would be negative 1 over 1, which is negative 1. So this appears to be negative 1.5 plus, I think that's going to be positive 1.5. That may be 0. In fact, I'm certain it's 0.